and SDP 2022 program, that is recent advances in science and technology innovations. I thank each one of you all for supporting this program and present here. So first of all, I would like to welcome our principal scientist, chief resource person and co-chairman for this FDP program, Professor O.N. Tiwari sir. I welcome today's resource person, Dr. Bhunia, Department of Bioengineering, National Institute of Technology, Agartala, Tripura. So for giving this topic, that is the process development for secondary metabolite production and cost-benefit analysis. Also, I welcome Professor S. Krupanidhi, D, Natural Science and Applied Technology from BFSTR. Also, I welcome our professors from all the departments and the deans. Also, I welcome all the dignitaries, faculty, scholars, and students. So before going to the talk from Bhunia sir, I invite Ms. Shakira to read the brief profile of our resource person before giving his talk. Shakira, please.
Good morning to one and all. This is Shakira, studying BTech Biotechnology second year from Department of Biotechnology, BFSTR. I really feel this task of introducing today's guest speaker, Dr. Bhunia, as a great privilege, sir. Dr. Biswanath is currently working as Assistant Professor, Department of Bioengineering, National Institute of Technology, Agartala. He completed B.Pharm and M.Tech in Biotechnology from Jadavpur University, Kolkata. He received PhD in Biotechnology from National Institute of Technology, Durgapur in the year 2012. Following his PhD, he joined to academia as Assistant Professor in Department of Bioengineering at National Institute of Technology, Agartala in the year 2013. He received DST Fast Track Young Scientist Award and CSIR RA Fellowship in 2012. Dr. Biswanath is working on various secondary metabolites production using fungal, bacterial, cyanobacterial, and algal strains. His research area is focused on bioprocess engineering, environmental biotechnology, pharmaceutical biotechnology, and bioinformatics. He assisted in development of proposed syllabus for PG program Pharmaceutical Biotechnology to South Gujarat University in 2007. Dr. Biswanath was a member of Advisory Committee of National Seminar on Recent Advances and Scope in Herbal Technology, Challenges and Prospects from 9 to 10 September in 2016. He is the member of International Conference Scientific Committee on Food and Biosystems Engineering in 2017. Dr. Biswanath is a visiting faculty to Professor Sri G.M. Bilakia College of Applied Sciences, Vapi, Gujarat, Department of Biotechnology, DIT Mesra, Department of Biotechnology and Bioinformatics at North Eastern Hill University, Shillong. Dr. Biswanath is a reviewer for several journals like Scientific Reports, Nature Group, ACS Sustainable Chemistry and Engineering, ACS Group, Renewable and Sustainable Energy Reviews, Elsevier, Journal of Applied Statistics, Carbohydrate Research, Process Biochemistry, Industrial Crops and Products, Biomass and Bioenergy, International Journal of Biological Macromolecules, Carbohydrate Polymers, Journal of the Taiwan Institute of Chemical Engineers, Desalination and Water Treatment, Water Science and Technology, IWA Publishing, Journal of the Institution of Engineers, India, Series E, International Journal of Biomedical Engineering and Technology, Egyptian Journal of Biological Pest Control, Journal of Food Science and Technology, Biomass Conversion and Biorefinery, Water and Environmental Journal. Dr. Biswanath has published more than 70 articles in high impact factor journals, 15 book chapters, and edited one book. He presented his papers in national and international conferences on topics ranging from bioprocess engineering, bioinformatics, enzyme and microbial technology, advanced purification process, and modeling. Dr. Biswanath Bhunia was a guest editor to recent patents on biotechnology scopus under special thematic issues on international enzyme and emerging area in 2017. Dr. Biswanath is editorial board member of Open Enzyme Innovation Journal under Bentham Science 2018, Current Biochemical Engineering under Bentham Science 2019, and Current Pharmaceutical Biotechnology under Bentham Science 2020. We all really feel very blessed to have you here on this wonderful day, sir. I now request Dr. Bhunia to give his lecture on process development for secondary metabolite production and cost benefit analysis. Sir, please.
Thank you. Good morning to all of you. Thanks, Shakira, for your warm introduction. I would like to thank organizer, faculty members of the Department of Biotechnology, Vignan Foundation for Science, Technology and Research, Telangana, Andhra Pradesh, especially Dr. Bobby, Associate Professor and Coordinator, Professor T.C. Venkatrasulu, a Chairman and HOD of the Department, Professor S. Trupatidi, Deans and other coordinators, Dr. Wen Thierry, Chief Scientist of ICRIR in New Delhi, for giving me an opportunity to share my thoughts on 5 days faculty development program on recent advances in science and technology innovation through online mode. I welcome all the participants, including faculty members, researchers, scientists, and students for this session. I would like to discuss on the process development for secondary metabolite production and cost benefit analysis. Today, that part, not overall the secondary metabolites from various sources. Very focusedly, I will discuss on the bacterial systems, microbial systems, fungal systems, or algal systems, cyanobacteria. So that means only microbial systems I will discuss. How can I develop a process? And cost benefit analysis of the entire process. From here, we can able to understand that products which is produced on process that can be commercially viable or not. So, what is secondary metabolites? So that is basically it is produced in the lead growth phase or stationary phase, people say, and it's organic molecules. Its molecular weight depends up to 300 kD, that is the molecular weight, organic molecules, and it not directly involve on the growth of microorganisms. Basically, it helps for its defense of the microorganisms. So understood the scenario of the secondary metabolite productions when microorganisms feel stress, and that stress can be manipulated, that can be done, and productions of metabolites, secondary metabolites can be enhanced. So why we are going for secondary metabolites production? Because most of the biological active compounds such as antibiotics, pigments, enzymes, enzyme inhibitors, so all are under the class of the secondary metabolites. And if you see the structure of the secondary metabolites, that complex structure you cannot able to synthesize by the chemical process or chemical synthesize, you cannot chemically synthesize because the structure is very complex. If you're talking about the erythromycins, penicillin G, these are very complex structure. Talking about the lovastatins, so statin group starts, all are the very complex thing. So you cannot able to synthesize. So you can use the bacterial platforms. From here it can be produced shortly with appropriate designing of the process or intensifying the existing process. There are few classes of the secondary metabolites, mainly primary microbial source, which is produced from the microbial source. You know that actinobacteria that are mostly prone to produce the antibiotics. Out of 6,000 antibiotics, 4,000 antibiotics are produced by the actinobacteria. And Bacillus and Pseudomonas are the prokaryote systems also can able to produce. Fungal aspergillus groups that is very much prone to synthesize the secondary metabolites. When you are talking about the anti-tumor agents, that actinomycin D or doxorubicin, these are the anti-tumors or that agents that is mostly produced by the actinobacteria. The microbial kingdoms, they are having contributed around 25% of the total secondary, although the secondary metabolites produced by the plants kingdoms are higher in range. Now, when we are talking about the pharmacological and nutraceuticals agents, already we have discussed about the statin group drugs, that lovastatins, simvastatins. So all of the statins, the initial parent lovastatins, that is produced from the Aspergillus teras, that is the fungal strain, from where that statin group drug is produced. And when you are talking about the immunosuppressive agents, rapamycin, pseudomonas, that are coming from the streptomycetes groups, cyclosporins, these are the produced by the fungal systems. When you're talking about the enzymes, as you know that most of the enzymes are produced by the Bacillus species or Aspergillus, Niger Aspergillus species. They can able to contribute a huge amount of the industrial enzymes. Its annual price is around $2.3 billion. And most important enzymes which having the commercial impact, that is proteins, and that is produced by the Bacillus subtilis or Bacillus licheniformis. They are the main dominating production. And Aspergillus niger also the important group of fungi that can able to also produce Aspergillus groups. They can also produce the commercial enzymes. And when you're talking about the enzyme inhibitors, nowadays you know that when the capsules that came to
मेरा और पापा का खाना नहीं बनेगा.
When the capsules came to, they know about that antibiotics, penicillin, ampicillin is coming with the clavulanic acid. So you know the clavulanic acid, that is basically beta lactalase inhibitors, and that is also produced by the that's streptomycin groups. That is also a type of secondary metabolites. Now I have enlisted from the literature that which is coming from actinobacteria, which is coming from the pseudomonas, which is coming from the bacillus, which is coming from fungi. But actinobacteria is the dominating candidate for industrial producer of secondary metabolites. When you are talking about the microbial secondary metabolites, and we should know why we are talking for the microbials. What is the advantage? All the plant kingdom play major roles for productions of secondary metabolites. Then why we are thinking for the microbial systems? What is the advantage there? Definitely its growth rate is very high. So you can produce the huge amount of secondary metabolites with short period of time. That is definitely advantage. Second advantage is that you can manipulate the media and you can optimize the process. Not only the manipulation of the media, you can manipulate genetic level too. So that's the beauty of this of when you handle the microbial systems. Another important part is that some complex structure which is produced by the certain microorganisms. It's an intrinsic property of the microorganisms never produced by other systems, animal and plant systems. In that case, you have to take into consideration that microbial systems are more appropriate for large-scale production or commercial viability concern. Now, you may think about that the manipulations of the process is a hectic work. When you are thinking for commercial productions of these secondary metabolites using microbial systems, then you have to know what is the process, what is the design concern, what is the reaction engineering behind that. Because when you're talking about the process, then there are two parts. One is upstream process, another is downstream process. Downstream process means after productions, you are purifying, you are characterizing, so whatever you are doing, starting from the centrifugations, filtrations, precipitations, dialysis, chromatography. So whatever you are doing, final thing is the either dryings you have to go for, or you have to go for the crystallizations before packaging and selling. So these are the downstream part, and you can manipulate, you can intensify the process. Most of the cases it has been found for 60% of the total cost that you have to contribute for downstream process. And another is upstream. So upstream means here all are will be taken into considerations, starting from raw materials, whatever you are using, whatever the pre-treatments if you do, or what process you are going to design. So process means there is a changing of chemical identity of the molecules. So whatever the reactants you are using, that is basically helps to grow the microorganisms. So here biomass production will be done. Parallelly, if it is the secondary metabolites, then from the biomass, your product will be formed. So these are the events, and that is the biochemical process where molecules change its identity. What are the molecules? The reactants, substrate. Why I'm telling why they are changing its identity? Because formations of the biomass is what happens here. So let us discuss on this biochemical reactions, what is going to happen. Because on that basis, you have to design a reactants, which will decide at which time, what time your product will be. It's a very core part of the bioprocess engineering. When we talking about the reactor design, when you are talking about the reaction engineering perspective, reactor designs means if you are talking about the batch process, the time requirements, how long time it requires to complete the batch or productions of certain amount of products. You initiate it in the reactors, and how long time it is required to get such amount of the products. So this is the reactor designs, and on which basis I will design the reactors. Definitely, you have to know that rate law, but before that, that should be it should be clear that the uniformity of the mass inside the reactor should be. Why I'm telling, because if you see that rate law, when a reaction is going to happen, where the product formation is going to happen, dP by dt, that rate law depends on the two parameter only. One is rate constant, another is concentrations of the reactant. We know that our biochemical process is the first order reactions. So first order means dP by dt is equal to K into C. Everybody know this equation. This is elementary rate law. And the concentration of the reactant, that should be uniformly distributed. And for that, whatever you need, you do that. If your mass is not uniformly distributed, so reaction engineering principle will not be applicable. So that is the prime agenda when you design a reactors. Mass and temperature should be uniformly distributed. Why I'm talking about the temperature? Because any reactions, rate constant depend on the temperature. If you are looking for a particular amount of product at certain times interval, then your rate constant value, that need to be constant throughout the process. And then it need to be fixed with temperature. So temperature should not be changed during the process. And another important part, you know that every microorganism, they need certain amount of temperature. So if you more than that, your catalyst will die. So that is also another concept, that temperature should be uniformly distributed. But what we understand from that, what we understanding is, and process design will understand that what type of products is forming. If it is the secondary metabolites, then where it is produced, in the log phase, early log phase, or stationary phase. In bioprocess, there is 3 classes. Either it is produced in the stationary phase, mostly secondary metabolites. Primary metabolites, they will produce in the log phase. And some metabolites, they are produced in the either log, either stationary, or in both. That is mixed phase. So there is a classification, and what my observation, what I have seen, that most of the secondary metabolites are producing in the mixed phase. They started from the that in the late log phases and ending with the stationary phase. So now if you are as an engineer, when you are handling a systems, you are designing a process, when you are designing a reactor, then your mind should be focused on either reactor design or process design. If you are fixed in the process design, then your answer should be, is it batch process or it will be in the fed batch process? The history of fed batch process, everybody knows. When penicillin G came to the market, then everybody has started to produce the penicillin G from the penicillin disogenum in the batch process, but they failed. Because that the most of the secondary metabolite penicillin G also, it is produced in the stationary phase. So basic rule of the stationary phase is the rate constant value should be 0. There is no growth, no net growth of the bacteria or fungi or microorganisms. So that's why when we starting the discussion of the kinetics and reactor design, kinetic part will tell you that what type of reaction it is and how the rate constant can be help for reactor designs. But process, that can be understood from the type of metabolites. So let us start to discuss on that. When we evaluate any process, so basically what we do it in the lab scale. In the sec flux, we do the work. Initially, we need to find a good candidate which you are looking for particular metabolites. Let you are looking for particular enzymes production from any strains, and you are very lucky that you got the good strains and you need to produce in the large scale. So what we do basically, we'll inoculate in the medium and waiting for understanding the data. So various time interval will collect the data. So mainly in the log phase, we collect the data. We calculate the rate constant value. In reaction engineering, rate constant in bioprocessing, its name is specific growth rate. So we calculate and we understand the relationship. What basically do that done by the Monod, and that is called the father of biochemical engineering. And he gave the law that is called the Monod law. Everybody knows. What is observation here? Observation is very peculiar terms. In reaction engineering, it never. Reaction engineering law is rate constant, does not depend on the concentration. But Monod show that it depends. It depends at certain levels. But when we collect the data and want to fit in the Monod models, what we observe that it's not properly fitted. So what is happening? What is the observation of the data? If you spell clearly, you will see that as the substrate concentration increases, initially it increases, sometimes remain constant, and then it is reduced. That is means your substrate level inhibition is going to happen, and that's why you have to study for another equations. those are it's available in the field, biochemical field. This is Andrews, Iva. Everybody knows about the Handel models, that is Edward models, computative revisited models. So these are the very common models. Everybody want to try to fit the data is whatever the data they got. So what data basically? Data means what about the specific growth rate? That how can I calculate? Simple basic rate law. That is 1 by x dx by dt. So collect the data, put into the equations. It is properly fitted or not. So how can I fit this? How can I make this? So you use the softwares, or you can manually, it take times. So what we observe, interesting, observe that Andrews models or IVA models is properly fitted. That means the nature of the process, nature of the systems, what Andrews proposed. So that is properly maintained here. So we understand what an Andrew model do, what is the natures, at what concentration I need to maintain. So that also helps to in the reactor design. So here you can understand in the Andrews models where the Q1 terms is very important term, that is the inhibited constants, and up to this is a monod models, but additional terms is here. So you understand if the Q1 value is high, then your inhibition should be very high. So most of the carbon sources that you need to check which carbon source having less Ki value, so that I need to keep into considerations. K's value will tell you the affinity of the microorganism towards the substrates. So that the process you have to find out the value of mu. Another important terms, not only the biomass is growing, but at which rate your substrate is consumed. So if your substrate is totally exhausted within 10 hours and you are designing the process for 20 hours, so no microorganism will be there in the system, it will be died. So you need to think about at which rate your substrate is consumed. There are three parts. When you are talking about substrate is consumed, there are three parts. One part is your substrate is dedicatedly going for growth of bacteria. Your substrate will be go for direct product formation. Your substrate will go for the maintenance. But when you are talking about the secondary metabolites, then definitely your reactant is not directly gone to the secondary metabolites. So definitely that part, substrate is going for utilizations of the product formation. It will not be applicable there. So definitely that will be the dp by dt will be 0. So this is the common equations, whatever we used for calculations of maintenance, because there is some maintenance amount of substrate that need to be given when you are designing reactors, at which rate your substrate will be exhausted. Because maintenance part you cannot ignore. There are certain bacteria needs the more amount of maintenance charge. So that will be deployed. Either your systems will be very unstable after sometimes. So here another part that is very important to calculate what is the value of the yield coefficients. So how much product will be formed, how much biomass will be formed from unit grams of the substrate if I contribute. So that is very important, and that can be for the bacterial system, it is varied from 0.5 to 0.7, but fungal system is very low. So that also taken into consideration when you are designing reactors. So I already mentioned in the stationary phase when you are talking about, you just see there is a no growth because death rate and growth rate both are equals. Is it under steady state? That conditions. Growth is in understeady. So here the maintenance only used in the stationary phase, because whatever the substrate will be given there, that will contribute for maintenance on. So in this way, you have to calculate each and every parameters which is required for the design of the for designing a process for productions of the secondary metabolites. So I'm just giving the data that is from my works for the enzyme productions that already have this. It's very interesting models that is product formation kinetics. So where we are we are basically want to know that at which rate our product is formed and what process I need to maintain. So unnecessary, if you go for the batch process, you will not get the desired amount of product. Even you may not get the products. That also I'll show you with examples. You may not get the products. So designing, when you are designing a process, then 2000 Liu-Dicking and period gave a models that is called the Liu-Dicking period models. What the model says, if you make a plot that 1 by x dp by dt, that is called the new, everybody knows, I hope so, that dp by dt is equal to alpha dx by dt plus beta x, where the alpha is called the growth associated constant and beta is called the non-growth associated constant. So when you are making plot mu versus mu, there are three type of plots. That might be possible of three plots. One plot will go through the origins. That means is a primary metabolites. Another maybe the straight lines. That is the secondary metabolites. Or it can some intersect. That means it is either produced in the log phase as well as stationary phase. Then if this condition arises, then what you will do? So just see this phenomena, what we observe in our cases. When you are went for xylanase production, what we found that y is equal to 18.045x, that's alpha value. That means certain amount of enzyme is produced in the log phase and certain amount, huge amount of produced in the stationary phase. If it is there, then how can you develop a process? That means few times you have to contribute for the batch process and then went for the fed batch process. So what is the difference between batch and fed batch? Why bacteria loves batch process than the fed batch process? Because batch process, initially you are giving huge amount of foods. Huge amount of food is there, so bacteria initially get the huge amount of food. They will multiply, grow. And after sometimes when they will understand there is no food, then they will get the stress, and that is the stationary phase where they will produce the secondary metabolites. What is the fed batch process? Fed batch process is we are not giving food enough amount. We are giving the limited amount of foods and certain time intervals we are giving food. So what is the beauty of this process? Every time we are giving the stress that food is limited, food is limited, food is limited. So whatever the food is there, only you can survive, but there will be no multiplications. So you know that fed batch process is called the quasi-steady state and batch process is called the unsteady state process. So definitely when your process, what is your demand? So if the alpha value is very high and beta value is 0 or tends to 0, then go for the batch process, you will get the huge amount of metabolites. When the beta value is very high, then go for the fed batch process, you will get the huge amount of products. But when there is certain amount of alpha value and beta value, then you cannot ignore the batch process. So you have to go for batch process and then fed batch process. So one examples we are sharing here. We started the work on the xylanase production from Aspergillus niger, and we isolated the strain. That part we are not discuss here, but our objective is that enzymes we need to develop. How we can develop the process? So fungus, if you see fungus Aspergillus niger, basically, if you grow in the PDA media, potato dextrogegal media, within 3 days they will show like this picture. After 7 days, it's become the spore. So why spore forms? Because solid state fermentation. So here the nutrient which was available in the solid phase, that is totally exhausted. Now another thing is that if you put this spore in the right environment, so what will happen? That spore will start to germinate and it will form the germination tube. So first of all, you have to know the morphology, which has aspergillus, which aspergillus has. That is the germination tubes. They will produce the germination tube within 6 hours. 3 to 6 hours they will produce in the liquid media. And then they will produce the hyphae. And after that, they will produce the mycelia. But mycelia, if you give the more food, they will create the more complex structure. Few observation, what we got. Because without knowing that, what is the new part, new research on the fungal systems, that how can you manage the systems? Because once complex will form, then you cannot able to manage. And very unfortunately, all the morphology, they will not produce the secondary metabolites. You are talking about penicillin, you are talking about enzymes. If you think from the aspergillus, these morphology never produce any secondary metabolites. So you are thinking that growth has come, so product will form. It never. So why? Because when the huge amount of growth will be, they will produce acid, and which basically inhibit the growth of the fungi. That is the main problem in the fungi system. Second problem is that these morphology will not produce secondary metabolites. Constant stress you need to give. And that state is not the limited states. The mechanical states you have to give, so that it can produce beads. And that also I'll show you. And that beads will produce the secondary metabolites. Now, these problems also similarly faced when the penicillins came to the market. Penicillin chrysogenum came to markets. People tried a lot in the batch fermentation process, but they did not get huge amount. Then went for the fed batch process. So here also we similar observation we found. Without bead formations, you cannot get a single that huge amount of enzymes. So what we did basically, we thought from the beginning we'll give the stress. So what are stress I give and where I give the stress? So when we start the and design any process, initially the preservation of microorganism is very important. Then the seed cultivation process, that is also very much important. Third one is the production process. These three things are in queue. If you only think you will design the production process, then you may not get the exact amount, or you may lose the global reach amount. So everywhere we need to give the stress. So initial from the beginning, if you put the stress to the microorganisms or fungi, say that constantly they will able to adjust with the environments. So here we start from the preservation stage. From the beginning, we put the stress. We thought, why you will preserve the microorganism for 7 days? Because spore will form. But if you keep longer times, maybe 14 days, maybe 28 days, 42 days, 50. So these days we did the experiments. And what observation we found? Spores means that having some foods, but that only to maintain the metabolic activity. But even if keep in the refrigerating systems, up to 42 hours, 42 days, it will slowly enlarge. But after that, it will reduce. So that observation is very much important, because we already start the germination process in the refrigeration condition. And if we could minimize the seed cultivation process, then in the production process, we can able to manipulate. So what is our observation here? We keep in the refrigerating systems, whatever observation we found, that up to 42 hours that you can. Next, we went for the seed cultivations. What we observe, that is very important part, because when you start the seed cultivation process, you even don't know when I need to finish this process. So there should be some marker to understand. Looking this marker, you can say, okay, I need to finish the seed cultivation process. There are two tools we have used. One is fixed temperature, another is fixed pH. So what we found that that temperature, if you could maintain 28 degrees centigrade and pH, initial pH is 7, then the final pH after 18 hours will be around 6. So if you test only pH of the media, then you will understand. Do not go for further for seed cultivation. So here our observation microscopically we observe that germination tubes that is elongated around 195.5 microns. So that is given for both cases. So if you maintain 18 hours seed cultivation. Initially we tried for 24 hours. When we keep the spore for 7 days in the refrigerating systems. So here we shorten the seed cultivation process. So whatever the electric bills, manpower that is required, that will be reduced. So intensifying of the process. Now you just see what is our motto. Our motto is in seed cultivations, fungi should not get any mycelial forms. It might be in the hype stage, but not mycelial. If it is mycelial stage, then you never control it in the production media. So what our observations, what we standardize in our lab that within 18 hours, so you will get the hype, but not in the mycelia forms. Now, definitely, when we are designing a process in the reactors, there are we know that we need to put the mechanical stress. Already I have mentioned that in fungi, if you want to use for the productions of any secondary metabolites, then without mechanical stress, they will not supposed to control. So what is the meaning of mechanical stress? Here, the impeller. What type of impeller is? How many type of impeller I will take? So what are the numbers of how many numbers of impeller I will take in the reactors? What are the parts? That also very important to understand. So if your impeller is turbine types, or it might be the Ruston type turbines. So usually we use the Ruston type turbine in the reactors. So what is the picture of the Ruston type turbine? If you see, this is a Ruston type turbines, and here the microbial damage will be very less. But if you increase the speed, that will cut into the small piece of the fungi, not bacteria, it's a fungi, special type of impellers. But its NP value is very high. What about the NP value? That is specific value that indicates the power. So how much electric bill you need to pay for this impellers? That is also very much important. If you increase the agitation speed, let you need the want to pay the mechanical stress to the fungi, then definitely you have to pay some electric bill more. So here you can see that previous cases. Normally we use the radial type impeller, so you can understand the impeller when it rotates. The water flow that will be in the radial direction, and it will hit the walls. It will distribute it in the two portions, and that height is called the clearance of the impellers. So if that amount of clearance can be made by this impeller, then a single impeller is sufficient. If you are not able, then normally you can increase the number of impellers. But thumb rule is 1/3 of the total height of the reactors. That is the clearance of the impeller. Now you just see that this is not a axial type. So here the top to bottom mixing is not possible. So first part I told that mixing is very important. If it is not properly mixed, you never desired the never expect the desired amount of product to be produced within the times. So that's why the impeller is very important. Now another problems when we face in the reactors, that is if it is aerobic systems, if it is aerobic systems, so that means the bacteria or fungi needs oxygen, and you are sparging with oxygen, and your impellers is in low speed. Then what happens? The impeller will not move, and that is also one problem. So that is called the flooding condition of the impeller. Then you have to increase the impeller speed. And the second picture, that is B, that indicates is the loading situation. If you increase more than that, then only impeller will move. Third case, you just see the air bubbles are completely dispersed. So why I'm talking about the air bubbles? Because the system is aerobic. And when you are purging, that means additional electric bill you have to pay for the impellers to move or to disperse the whole bubbles inside the reactors. So what basically problems are in the gas bubble systems? Everybody know this is three-phase systems. If there are multiple phase, it is a heterogeneous systems. Heterogeneous system means concentration gradients will be this. Problem is oxygen is sparingly soluble. Oxygen is sparingly soluble in the system. So if the oxygen is sparingly soluble, then what happened? There is a resistance between the two layers, and oxygen will not move because the concentration will be reduced in the liquid system. So here you need to increase the impeller speed, and that impeller speed will identify by the KLA value. I hope that amount of KLA is the product of KL into A. KL is the mass transfer coefficient, A is the interfacial area. That is ratio of the area by volumes. So that can be, if your KLA value is very high in the systems, then that means your reactor is sufficient amount of oxygen capacity. Either what happened in the gas systems, you are giving huge amount of foods, and fungi are growing huge amount of oxygen demand that cannot be supplied, and that is also problem when penicillin G production started in the batch reactors. So that also need to take into consideration when you go for. So what we observe in the batch process, that 16.1625 units xylenase we are able to produce using the batch process. But you know that most of the cases, what a laboratory do, that is called the one variable at a time methods. What are the parameters they identify that is required for the optimizations of the batch process? They keep all the parameters constant, so only one factor they change, and in this way they optimize the process. This is called change one variable at a time. But it has a limitation. Limitation is the number of experiments is high, labor cost is high, you never get the real optima because interactions are missing. That's why people are using nowadays the statistical tools, that is either response surface methodology or Taguchi methodology. Response surface methodology, that CCD design is more important nowadays that people are using. Although nowadays artificial neural network has come, but ultimate thing is that when you start for the optimizing any process, you have to identify the factors and the level that need to be screened. Is there exactly what about the factors they have screened is properly screened or not? If it is properly established, then go for the response surface methodology optimization. That is nothing but a polynomial equations, and you have to see there is a interaction parameter is considered xi into xj. So these are the constants, beta's values are constants. You have to solve this equation. Nowadays software is there. Whatever the data you will get, you put it, and you will get the equation and get the optimum condition. But definitely the response surface methodology, what is my observation here, you will get the real optimum value, but number of experiments is high. And second problem is here that you will not get that you are not considering the standard deviations of the process, because sometimes more standard deviation you are thinking the mean value is the main. No, standard deviation also need to consider. In the Taguchi methodology, what they are using here, you may miss out the real optimum, but it approaches to optimum. Here, analysis is done by the signal by noise. Signal is the mean value, but noise is the standard deviations. So here, on that basis, that optimization is done, but number of experiment is less in compared to the response surface methodology. So this is the advantage for the Taguchi methodology and response surface methodology too. Now, when we are designing a fed batch process, after designing the batch process, you go for the fed batch process. What are the disadvantages I already told in the batch process, and what are the advantages I told in the fed batch process. Here, continuous amount of food you have to give in certain time intervals, and it is a quasi-steady state. That means your concentration will not change, but your mass will be changed because your volume is changing. That is the things. At the rate you are giving, but the rate should be equal to the specific growth rate. Only this thing you have to calculate. What is the specific growth rate of the microorganisms? That should be equal to the dilution. What is dilution? Dilution is F by V. What is F? That is feed rate. V is the volume. Just divide it, you will get the mu value. You will get the T value. So accordingly, you have to design the process, because fed-based process means a question first will come that at which rate you will start the experiments. What will be the feed rate? How does the initial value? So that need to be properly designed by the process engineers. So you have to design that. Thing is, mu should be equal to D. So here our motto is, I need to pay stress to the microorganism from 72 hours. Why I'm telling 72 hours? Because already I show you the alpha and beta value in the previous slides, that your secondary metabolites, which is produced by the fungus, then that should be batch process is there initially. So 72 hours batch process will run, and then we'll go for the feed batch process. So what are the batch process? You just observe the batch process. Your substrate concentration is drastically reduced within 72 hours. So what up to 72 hours, your substrate is totally exhausted. Then we start to feed batch process. Simple thing, mu is equal to D. What is the specific growth rate? And that amount of feed rate you give. And again, your substrate will be increased. Substrate concentration will be increased. But what about the substrate concentration initially? That is not maintained. That means every time I am giving stress to you, you produce the secondary metabolites. So after at 120 hours, again we are giving the foods. So foods is gradually exhausted. So in this way, you have to design the process. So the amount of food which you are giving, that basically will for your survival. So you cannot multiply. So what is our observation? That is one type of stress. But is this stress is sufficient for fungi? No. They will not produce any secondary metabolites at the larger amount. So what we did? You just see initially mechanical stress. That means agitation speed. We keep it 120 and up to 12 hours. Then we increase 48 hours is 150 RPMs. Then we increase 48 hours to 72 hours. So in this stage, up to 72 hours, you imagine the 72 hours, your food is exhausted. Your RPM is very high. Certain amount of micelle is formed. Now again we are increasing the impeller speed at 210. When 210 is started, then impeller is moving very fast, and your micelle will be chopped in the small pieces, and they will produce beads because they got huge stress by the mechanical agitator. They got huge stress and they start to form the beads. Now this bead forms will happen. That amount of bead formation will take place, and that beads only produce the secondary metabolites. So you just see continuous we are increasing the agitation speed. Now at 120 also again we are increasing the agitation speed, and it is around 240. So you just see starting with 120, gradually increasing the agitation speed, and 240 when it reaches complete micelle is converted to bits. But how it looks the bits, that's coming the next page. But if you complete conversions of bits can be done, then your production amount will be high. But there are two aspects here. First aspect, what will be the size of the bits, and second, what are the numbers of it. So size and number both will play major roles. If the bit size is very small and number is very high, your productions will be very high. Let us discuss on that. So here you can understand that there are, when we started the experiment at the initial pH, 7.5, 7 and 6.5, you will see that 6.5 huge amount of micelle is formed. 7 the less, 6.5 here also the micelle is less complex than the 6.5. So you know the fungus want to grow at pH 5 or near to 5. If you increase the pH, then definitely its growth will be inhibited. So what observation after 72 hours at pH 7.5 bit size is very small and 6.5 bit size is very high. After 144 hours, they just see the bit size. So that means if your bit size is big, that will not produce huge amount of enzymes. So that's why we took 7 and 7.5. But why we choose the that 7.7 is very important, because 7.5 the number of bits is very less. So ultimate the number and size both will play major roles for enzyme productions. So that what we observe, how we develop the process, we just see the process design part I have told, and the process design part, that which process I will take. Here batch process and fed batch process we have discussed. Batch process we got that's 1624 units, and fed batch process we got 2524 units. But only one thing, that 72 hours you have to give the food, and 1 to 2 hours you have to give the foods. So that's need to be maintained. Then you can increase the amount of child energy. So another part also I need to discuss, if the time permits, that Serratia martians. So we are also working on the prodigation. Is one colorants that having the anti-cancer activity, and that we are working on that, and how we can develop the process. The similar observations also we did for prodigiosis. When we are keeping the observation for 1 day, its production is going to count high. After that, it is reduced. Similar observations are like the secondary metabolites when you are subculturing. First time subculturing, you will get the huge amount of product. And second time you will do, then bacteria will not get the stress, because they understand it is my environment, good environment. So production will be less. So second picture indicates how your subculturing reduce the productions of secondary metabolites. Third, obviously pH. pH play major roles. That pH 6 to 7, that 2 pH is good for productions of the prodigation. And shocking period, again we are talking about the stress before going to the production media. If you keep 1 day, keep in the refrigerator for 1 day of the seed culture, you will see the production amount is very high. But other case, it is found reduced. We also worked on the various media we have tested, and we found the gluten broth is appropriate media, and 30 degrees centigrade is the optimum temperature. Peptone is the optimum nitrogen source, and lactose is the carbon source, best carbon source. Again, we have to understand that the media can manipulate or not. When in beginning we have discussed the why we are using the microwave systems, because we can manipulate the media. Here we tested with peanut 5%. We purchased from the market and grinding it, and then dry it, and we use 5%. And peanut and sesame also powder we have tested. We found that peanut is the best carbon source for productions of the producing. But one thing, one observation from here, when you're designing the process, solid state fermentation will be best for the secondary metabolite production, for this case, producing, because peanut is not used in the submerged fermentation. So now we are talking about the cost benefit analysis, because when you are preparing any media, any products, so you do not know that is commercially feasible or not. So your process and products both are commercially feasible or not. Then obviously you have to go for the cost benefit analysis. So cost benefit analysis means entire cost, whatever requires for. So what are the type of cost? Cost is what are the medias you are using, what are the consumables, ingredients that you have used. That's the one type of cost. This is chemical cost, consumable cost. So you will see that we have segregated all the things. There are three parts. One is Newton broth, we have estimated the cost. Second is the cost we have estimated for the sesame oil, sesame plus modified media 1. And third one is the peanut with the Newton drops. So what our observation we found that sesame, Newton broth produced 15 milligram per liter, sesame produced 33, that peanut produced 33 milligram per liter, and sesame produced 21 milligram per liter. So what are the entire cost came for 1 liter? If you produce in the 1 liter in the conical flask, 2 liter conical flask, so you will get that that amount of money you have to invest for productions of 15 milligrams. So not only the consumable cost, but also you think about the what is the electrical charge. So electrical for machines, because what about the machines you have used for the single batch process. So definitely that cost also you have to calculate how much, what is the watt, what is the hour taken, so what is the electric bill will be, that need to be converted and you have to add. And what is the electric charge per unit in Tripura, it is 9 INR. So that's commercial electric bills. That also you have to calculate for modified media, that is 421, because mixing grinders that is included when we are going for designing of the media 1 and media 2. So next we need to think about detailed establishment cost and management cost. So when you are designing process, definitely one house you have to take the range, and skill manpower supervisor is required, skill labor is required, and their cost that need to be calculated. So that is also here. And another part is the warehouse component. So once you are going to develop a single batch process, then warehouse components, one house where you need to store that fan, tube light, AC, computers, all the parts, manpower, cleaning, data operators, that need to be included when you are taking into considerations of the cost calculation. So next part is the depreciation cost. This is very important because when you are purchasing the fixed assets, and that basically 10% reduced. So every 10% that will be the annual depreciation cost. We have included all, and depreciation cost has been calculated. Next. Next part is depreciation cost, and next is the total sellable cost. So what about the cost we have added? So media consumable cost that we have calculated, cost of electricity, establishment cost, warehouse cost, total batch cost that you have to. Then downstream process, actually there's one scientist, they did the work on the production, and they told that 65% of the total batch cost will be your downstream cost. So downstream cost, upstream cost, and downstream cost is the total cost. Then you have to package and material handling around 15%. Then preservation and storage cost, and transport cost, and depreciation cost, dealer cost, product marketing cost, profit. So if you include all, your total price will be 265.45 INR rupees per milligrams, and 120 for the peanut, and 189 for sesame. Now we compare the market price. What are the market prices there? So Santa Cruz, they also produce the produce, and that's amount is 36,936 for 1 milligrams of the produce. You know that how much cost it is. It's very costly. But in our case, we show that that amount is reduced. So this is only the single batch process in the conical flask. But when we go for the fermentation, I hope that can be slightly reduced. So you understand the when we design a process, how much profit cost they are mentioned to 20%. When 20% cost, that is taking into profit cost, and that profit cost also if you put, then also our the production cost will be less. So that's why you have to understand the total cost estimations for any products or process which is commercially feasible or not. This is some saline research work that we did. What are the publication we have? I'm just sharing this publication. Last 5 years, what we did. These are my students. First, he completed his PhD and he did work on the xylanase. These are the students. Sudhanshu also completed bioremediations. Thank you for your patience. Now waiting for clarification.
Thank you, sir. Thank you for
Thank
your
you.
patience, sir. Thank you for giving very informative topic. Is there any questions from the audience, participants?
Bobby, Bobby madam, I have a question.
Yes.
Sir, Bhunia sir, excellent talk, sir. You have given complete information about production of xylanases and other parameters that are required along with the kinetic studies. One thing I have also worked on the xylanases and cellulases, sir. When we were working with Aspergillus niger, it have the capacity of producing both cellulases and xylanases simultaneously, sir.
No,
Hello,
madam.
sir.
I'm understanding, madam. Tell me, what is the query?
Actually, Aspergillus niger has the capacity of producing both cellulases and xylanases simultaneously.
Okay. But madam, what are the media?
So you are using Aspergillus niger. Yeah, we used PDA only, sir. So when you are using PDA means along with your xylanase, you will be getting your cellulases also in the crude extract.
Yes. No, madam.
Then how you are going to separate the?
No, in my case, I'm not using the PDA media. The PDA media we use for the maintenance purpose. But when we are going for the xylanase productions, only media we use the xylan, that is hemicellulase. If you use the xylan, then it will not produce any cellulase. And
yeah, if
that
you are
also,
using xylan, specifically if you are using xylan means okay, sir, it won't be because xylan. If you are using xylan, then it will be specifically producing xylanases. So
okay.
when we are talking about PDA means both will be produced. So
both
I have a doubt.
Yes.
Yeah. Okay, sir. If you are using xylan, it's fine, sir. There won't be any cellulase. Sir, what is the IU you have obtained, sir?
That 2,500 unit in after fed batch process.
Oh, 2,500 IU you have obtained, sir.
Yes, yes.
So it's a good. Then when we worked, we were able to go up to 300, 400 IU, sir.
400.
Only up to 300, 400.
On the calculation of unit, in my case, the calculation of unit is microgram of xylan is produced.
Okay.
Yeah, microgram of the xylan is produced. Microgram of the xylose is produced per minute per ml of fermentation crop. So that is the calculation of 1 unit of xylanase enzymes.
Okay,
so in your case, what is the protocol you have adapted, and that may be compared. Some cases, some scientists use that how much micromoles of the xylose is produced per minute of reaction. So that considers some cases, but in our cases, I'm telling, we got the 2,500 unit. The unit calculation is the microgram micromole of xylose is produced per minute of reaction per ml of fermentation drop. That is defined for 1 unit of xylose.
Okay. Sir. Thank you, sir. It's a very good presentation.
Sir, tell me.
Hello, sir.
Yes.
Hello. Sir, it's congratulations, sir, Professor Bishwant Bhunia.
Thank you.
So it was a nice presentation, and you have discussed more production aspects and then cost analysis. Sir, myself, Dr. Rangara Vambati, sir.
Yes,
So
sir.
I worked on more algal technologies from Vignan.
Hmm.
So I just want to ask you that the enzyme which produces, did you see the purification process, like a purification?
Yes,
And
yes.
then did you study any applications oriented commercial
Yes.
aspect?
Yes, sir. Actually, sir, when I started the discussion, I told that I only concentrated on the upstream. Downstream process, we did the ammonium sulfate precipitation, dialysis, then ion exchange chromatography, then gel chromatography, then we purified the proteins and we got that single band in this page, and its application is used in the fruit juice clarification. We patent also, we did one patent on that.
Okay, what about other pigments, sir? You mentioned another pigment that
That's
produces. Yeah.
Prodigation.
Yes. Did you
That is-
check some biological activities, any applications
Yes.
oriented?
Yes. It is already established, sir. It is not new. Prodigation is used for that. That new things we did not do. It is already established. It is a anti-cancer properties, and it is a antioxidant properties. These properties are there. That is already established. We did not do anything. So we only concentrate to development the process and cost analysis.
Okay. Thank you. Thank you very much.
Thank you, sir.
Any more questions from the participants? So I think there is no questions, sir. So thank you, Vishwanath, sir. Thank you
Thank
for
you.
your long and very valuable talk,
Thank you.
sir. It is very informative to us. Thank you for your time and presence, sir.
Okay. Thank you, ma'am.